In June 2018, OpenAI published a paper about a model called GPT-1. It had 117 million parameters, a number that sounds large until you hear what came next. The model was trained on book corpus, a dataset of about 7,000 unpublished books, totaling 4.5 gigabytes. That's less data than fits on a cheap thumb drive. And what this small model did was something no one had quite seen before. It took a single architecture, one design with no task-specific modifications, and outperformed models that had been hand-built for individual problems: textual entailment, semantic similarity, question answering. Specialists beaten by a generalist. The people who built it hadn't set out to prove that generalists could win. They'd set out to see what a transformer could do if you just let it read.
And it's worth pausing on what that means structurally. Before GPT-1, the way you built an AI system for, say, detecting whether two sentences meant the same thing, you designed a model for that specific task. You gathered data labeled for that specific task. You trained it on that specific task. If you wanted it to answer questions instead, you started over. Different architecture, different data, different training. GPT-1 said, what if you don't do any of that? What if you train one model to predict the next word over and over on a pile of books and then just point it at a new problem?
And it worked. Not perfectly, not overwhelmingly, but well enough to beat the specialists. That was the signal. One model, one training process, many tasks. The transformer architecture that Google's researchers had published the year before, the one whose 8 authors would all eventually leave the company, had found its first real application outside translation. OpenAI had picked up the baton.
So what happens when you take that same idea and make it bigger?
GPT-2 happened, February 2019. Same architecture, fundamentally the same approach, predict the next word, but now with 1.5 billion parameters instead of 117 million. Trained not on 7,000 books, but on 40 gigabytes of web text, a dataset OpenAI built by scraping every outbound link from Reddit posts with at least 3 upvotes. And GPT-2 did something GPT-1 could not. It performed tasks it had never been shown how to do. Zero-shot capability, meaning you could hand it a prompt it had never encountered during training, with no examples, no fine-tuning, no adjustment of any kind, and it would produce coherent output. Write a news article, summarize a passage, answer a question about a text it had just been given. Not reliably, not always correctly, but coherently.
And that coherence scared them.
It did. OpenAI made a decision that had no precedent in AI research. They staged the release. They published the paper describing GPT-2, but withheld the full model. First, they released a version with 117 million parameters, the size of GPT-1. Then a 345 million parameter version, then 774. They didn't release the full 1.5 billion parameter model until November 2019, 9 months after the paper. Their stated reason was explicit. They believed the model could be used to generate misleading text at scale, and they wanted to study the risks before making it available. This was the first time in the history of artificial intelligence that a research organization refused to release its own work because it considered the work too dangerous.
And there's something quietly important about that decision because it tells you what OpenAI believed about their own creation. They weren't worried that GPT-2 was too good. They were worried that it was good enough to fool people, good enough to generate text that could pass for human writing in contexts that matter: disinformation, spam, impersonation. The model wasn't thinking, it was predicting words, but its predictions were smooth enough to deceive.
Then came GPT-3, June 2020, and this is where the numbers start to lose meaning for most people. So, let me put it plainly. GPT-1 had 117 million parameters. GPT-2 had 1.5 billion. GPT-3 had 175 billion. That's not a smooth escalation. That's two jumps, each roughly an order of magnitude larger than anyone had attempted before. The training data was enormous, 60% filtered common crawl, which is essentially a snapshot of the public internet, plus web text, 2 different book corpora, and Wikipedia. Lambda Labs estimated the training cost at $4.6 million, or 355 GPU years if you ran it on a single graphics card. And what GPT-3 demonstrated was a capability that genuinely surprised the people who built it: in-context learning.
In-context learning means the model could adapt to a task it had never been trained on, not by updating its internal settings, but purely from the examples you put in the prompt. You show it 3 examples of English sentences translated into French, and it translates the 4th one. You show it 2 math problems with solutions, and it attempts the 3rd. The model's weights, its internal parameters, don't change. It just reads the pattern you've given it and extends it. Sam Altman himself went public saying the hype was too much, that GPT-3 still had serious weaknesses. But the capability was real, and it raised an obvious question. And that public caution is worth remembering because it's the first appearance of a pattern Altman himself would repeat. Acknowledge the limits loudly, ship the product anyway, worry in public, scale in private. It's not hypocrisy, exactly. It may be genuinely held ambivalence, but the ambivalence never slows the deployment.
The question was, is this just about size? If you make the model bigger, does it keep getting better? And if so, how much bigger, and at what cost, and with how much data? That question had been lurking since GPT-1. In January 2020, 5 months before GPT-3's public release, 2 OpenAI researchers, Jared Kaplan and Sam McCandlish, published a paper that tried to answer it mathematically. The title was Scaling Laws for Language Models. What they found was striking. Language model performance, measured as prediction error, follows power laws across 7 orders of magnitude. Plot the loss against model size on a log scale, and you get a straight line. Plot it against data set, straight line. Plot it against compute, straight line. This wasn't a vague trend. It was a mathematical relationship that held across an enormous range.
And these power laws came with a specific prescription. If you had 10 times more compute to spend, Kaplan and McCandlish said you should make the model 5.5 times bigger, but only add about 1.8 times more data. In other words, spend your budget on parameters, not on feeding the model more text. This is exactly what OpenAI did with GPT-3. 175 billion parameters trained on 300 billion tokens, roughly 1.7 tokens per parameter. The scaling laws paper was the recipe, GPT-3 was the dish.
Now, here is where the relay race begins in earnest. A relay race across 5 organizations on 3 continents, a baton no one could hold. Because several of the people who discovered those scaling laws did not stay at OpenAI to apply them. Dario Amadei, who was VP of Research, Jared Kaplan, co-author of the Scaling Laws paper itself, Sam McCandlish, the other co-author, Tom Brown, lead author on the GPT-3 paper, Chris Olah, one of the most respected interpretability researchers in the field. Between 2020 and 2021, they left OpenAI, and they didn't scatter. They founded Anthropic. There's an irony that will matter later. Dario Amodi didn't just participate in GPT-3's development. By multiple accounts, he was one of the people who pushed hardest for the extreme scale of the training run, the decision to go to 175 billion parameters. The person who would found an AI safety company had, months earlier, been one of the most aggressive advocates for making the model as large as possible. Whether that's a contradiction or a conversion depends on when you think the lesson landed.
Think about what that means. The people who wrote the equation, the ones who showed the world that AI performance is a predictable function of scale, walked out the door and started a competing company built on the knowledge they generated. OpenAI funded the research, OpenAI published the research, and then OpenAI lost the researchers.
The pattern that's been running through this story since the beginning. The organizations that fund the breakthroughs never keep the people who make them. Google published the Transformer paper, all 8 authors left. Google acquired DeepMind and kept it at arm's length in London. Now OpenAI discovers the scaling laws, and the discoverers walk across the street and open a rival shop.
But the story doesn't stop there, because the scaling laws themselves turned out to be wrong. Not entirely wrong, directionally right, but wrong in a way that mattered enormously for anyone trying to build the next generation of models.
In March 2022, DeepMind, the lab Google had acquired 8 years earlier, the lab that built AlphaGo, published what became known as the Chinchilla paper. They ran over 400 training experiments, systematically varying model size and data quantity, and they found that Kaplan and McCandlish's exponents were off. The OpenAI scaling laws said, given more compute, invest most of it in making the model bigger. The ratio was roughly 73% to parameters, 27% to data. DeepMind's correction said the split should be roughly equal, 50-50. Model size and data size should scale together.
This isn't an abstract mathematical disagreement. This changes what you actually build. Under the OpenAI scaling laws, you build enormous models and feed them relatively less data. Under DeepMind's correction, you build smaller models and feed them much more data. And DeepMind proved their point with a model called Chinchilla. 70 billion parameters, 4 times smaller than Gopher, DeepMind's own previous model, but trained on 1.4 trillion tokens using the same total compute. And Chinchilla beat Gopher on nearly every benchmark, 67.6% versus 60% on MMLU, 65.1 versus 54.4 on Big Bench. A model 1/4 the size, performing better because the compute was allocated correctly.
So count the handoffs. OpenAI takes Google's Transformer architecture and builds GPT. OpenAI researchers discover scaling laws. Those researchers leave and found Anthropic. DeepMind corrects the scaling laws. And then a fourth organization, Meta, takes DeepMind's correction and builds LLaMA. Each organization advanced the work. None of them held it for long.
And what's striking is that this wasn't a planned collaboration. Nobody designed this relay. Each handoff happened because people left, or because rival labs saw a flaw, or because a correction opened a door that the corrector themselves didn't walk through first. The knowledge moved faster than any institution could contain it.
While this relay race was playing out in research papers and corporate departures, something else was happening that almost nobody outside the software industry noticed. On June 29, 2021, GitHub, owned by Microsoft, which had invested $1 billion in OpenAI, launched a product called Copilot.
Copilot was powered by a model called Codex, which was a variant of GPT-3 that had been fine-tuned on 159 gigabytes of Python code scraped from 54 million public repositories. What it did was simple to describe. It sat inside a developer's text editor, Visual Studio Code specifically, and predicted what code you were about to write. You'd type a comment describing a function, and Copilot would write the function. You'd start a line, and it would finish it. You pressed Tab to accept.
This was, by 17 months, the first mass-market product built on a large language model. Not ChatGPT, not any chatbots, an autocomplete tool for programmers. And because it was embedded in a text editor, because it felt like a feature update rather than a revolution, it spread without the kind of public attention that later products would command. Within months of its release, over 1 million developers were using it. GitHub tested the generated code and found that only 0.1% appeared verbatim in the training data. The rest was genuinely synthesized. The Verge called it the first major result of Microsoft's billion-dollar investment in OpenAI.
And here's what I think most people miss about Copilot's significance. It wasn't presented as artificial intelligence. There was no press conference about machine consciousness, no Senate hearing, no existential debate. It was a tab key. You pressed Tab and the code appeared. 1 million developers started using an LLM every single day, and the public conversation about AI hadn't even started yet.
The tab key is the detail that matters, because it tells you something about how transformative technology actually enters the world, not with a declaration, not with a warning, with a feature that saves you 30 seconds embedded in a tool you already use, adopted by people who are too busy to ask what's powering it.
By the middle of 2021, the landscape looked like this. The transformer architecture had moved from Google to OpenAI. The scaling laws had been discovered, published, acted upon, and then corrected by a rival lab. The people who wrote the laws had left to start their own company. A fourth organization was about to apply the correction, and 1 million developers were pressing Tab to accept code written by a machine that was predicting their intentions from context. All of this had happened. None of it had reached the general public.
A tab key quietly rewired how 1 million developers worked. Nobody noticed. That was about to change. Next, on how AI happened, Google's own engineers had a name for their chatbot. They called it a pathological liar. They said it gave advice on landing planes and scuba diving that could get people killed. And then Google shipped it anyway, because not shipping felt worse. I'm Knox. Every Saturday on Pulse Deep Dive, one story, the history, the present, and what comes next. Find it wherever you listen.
How AI Happened is produced by Singularity Pulse Network. This series is for informational and educational purposes only. Historical accounts are sourced from published research, reporting, and public record. Some timelines are condensed for narrative clarity. Nothing in this series constitutes legal, financial, or technical advice. Views expressed are those of the hosts and do not represent the positions of any organization mentioned. For sources and corrections, visit singularitypulse.network.